All right, so let's go back to sharing my whiteboard, and here's the result that we want for a primality test. Here's my theorem. Does this theorem have a name? Euler's criterion. So this is called Euler's criterion. Okay. If P is prime and A is an integer, then A raised to the P minus 1 divided by 2 is congruent to the Jacobi symbol of A over P mod P. That's Euler's criterion. If P is prime and A is an integer, then A raised to the P minus 1 over 2 is congruent to the Jacobi symbol of A over P mod P. This is not at all helpful right now for a primality test because it starts with the hypothesis if P is prime. And we don't know whether a number that we're trying to do a primality test on is prime or not. So we're going to look at the contrapositive, which is always true, and the converse, which is sometimes true. Here's the converse. Let's do contrapositive first, sorry. Let's do contrapositive first. So contrapositive is going to be if A to the P minus 1 over 2 is not congruent to the Jacobi symbol of A over P mod P, then P is not prime. Or A is not an integer, but we're just going to assume that A is an integer. So if A to the P minus 1 over 2 is not congruent to Jacobi symbol of A over P mod P, then P is not prime. And usually we use N rather than P. I should have written this with N's, but I don't want to erase everything because it's easier on the board than it is on a whiteboard here to erase. Because the conclusion is P is not prime, that's a little bit weird. So usually we use N's here instead of P's. This is the contrapositive, so this is always correct, right? It is the contrapositive, it's always correct. And our then could be stated as N or P, whatever you want to call it, is composite. So this goes back to our general method of dealing with probability tests and primality testing, right? Whenever we get composite out as an answer, we're guaranteed to have the correct answer. Same thing here. We know the contrapositive is correct, always, always. And so therefore, if we get an answer of composite out, as soon as we get to the Solovay-Strawson primality test, then we know our answer is correct. Here's the converse, which may or may not be true. So the converse is, I'll write it with N's. If A to the N minus 1 over 2 is congruent to the Jacobi symbol of A over N mod N. So if I do have a congruence, then N is prime. So this may or may not be correct. So if you get A to the N over 2 congruent to the Jacobi symbol of A over N mod N, then N is prime. This may or may not be correct. Once again, this goes with the same idea that we've had with primality testing. If we get an answer of prime out, we're not sure whether our answer is correct or not. Same thing here. We're dealing with the converse, so we're not sure if our answer is correct or not, because sometimes the converse is true and sometimes it's not. And if you get a wrong output with A and N, in other words, if you get an output of prime when N is actually composite, So if you get a wrong output, if you get an output of prime when you actually have composite, then the terminology is that A is an Euler liar for n. That's your terminology. So this is kind of like the pseudoprime and the strong pseudoprime to the base A that we had. These are called Euler liars because we are dealing with Euler's criterion. So A is an Euler liar for n if you get a wrong output out. It's kind of cool for terminology. I kind of like it. A is an Euler liar for n. Euler liar. Okay. All right, let me see all of you again just for a minute. Any questions up to that point? Doing good? Give me a thumbs up. Makes sense? Doing good? Okay, I'm gonna pop up my slides that have the Solovay-Strassen primality test on them, just so you can see how the protocol works, but it's basically the same thing as what we just talked about in terms of calculating the Jacobi symbol and checking whether you have a congruence. So let me get my slides up here. There are pictures, by the way, if you would like them, Solovay and Strassen, and they do have first names. Hang on, let me find that on Wikipedia. Robert Solovay and Volker Strassen, and that's, I would guess that they are from one of the Swedish or Norway. I'm being very culturally insensitive, just guessing by their names, but that would be where I would guess they would be from. Okay, so Solovay and Strassen primality test. Here's your process. Again, this is exactly what we just talked about, so it should totally make sense. Choose a random value of A, where A is between 1 and n, and then if A to the n is not congruent, I have my mod on the other side. If A to the n minus 1 over 2 is not congruent to the Jacobi symbol, mod n, then you want to output composite, and otherwise you want to output prime. So again, totally what we just talked about. Totally what we just talked about. I want to run an example on Perry, and I do want to do this also so that I can show you how to compute the Jacobi symbol on Perry, because we are not computing the Jacobi symbol by hand, again, ever. But that's your test, and it doesn't matter which side the mod is on. Either side of the equation is fine for the mod, either way. If we want to talk about in Perry, the command, if you want, so to evaluate A over n in Perry, my command is Kronecker, Kronecker A, comma, n. That's my command, Kronecker in Perry A, comma, n. That's your command that you want in order to be able to evaluate the symbol in Perry. The reason for that is because the Jacobi function or the Jacobi symbol is sometimes also called the Kronecker delta symbol. They have slightly different processes. One requires A and n to be relatively prime, and the other does not. So they're slightly different, but they basically work the same way. And so that's the symbol that you want to use in Perry. I am not sure if Jacobi actually works in Perry or not, and we can try that in just a minute when we do some stuff on Perry here. And usually, two things. First of all, n is odd, because you're not going to test whether an even number is prime or composite. That's just stupid. You know the answer, right? So usually n is odd, and the reason that is important is because in my exponent here, I have A to the n minus 1 over 2, and if n is even, that's not a whole number. So we want to make sure that n is odd. And then usually also A is even, because then the GCD of A and n is equal to 1. And so also the Jacobi symbol then is not equal to 0. So usually, practically speaking, this is what we want to come up with when we are figuring out values for the test. We usually pick an even value of A so that we don't have to worry about getting 0 out for the Jacobi symbol and having some weird thing happen. Okay, any questions up to this point before we play with this on Perry, and I show you how this works. Anybody, anything up to this point? Now is a good time to ask. Does the concept make sense of using the contrapositive and the converse for primality test, composite, and prime? Give me a thumbs up. Yes, contrapositive and converse, that part makes sense. Okay, good. Any questions before we demonstrate this on Perry? Anybody, anything? Okay, let me then resize you so that I can get to Perry here. And let me stop annotating. And let me get out of this and erase my annotation, which I don't remember how to do. Who told me how to do that last time? I'm sorry. Annotate, clear, clear all drawings. There we go. I'm sorry. I will learn this eventually. I promise. It's just slow right now. Okay, let's do this in Perry. Here we go. Thank you for your patience while I am figuring this out. I've got most things down in Zoom, just not quite everything. All right, let's try one of these. So I'm going to go with the random value of n, and I have no idea whether it's going to be prime or composite. So here's my value of n. That's an odd number. That's great. Let's try a equals 2. Just to see what happens. We will go ahead and try that one there. And then what I want to do is, hang on, somebody has a question. Thank you, Daniel. You'll never get those 2.4 seconds back of me figuring how to unannotate my screen. That's great. Thank you. I'm going to figure out how to turn off your chat. Okay, here we go. I need to do a couple of things. So I need to do a power mod of, hang on, I need my notes out. I need to do a power mod of a to the n minus 1 divided by 2 and n. That's my first thing that I need to do. And then I need to do the Jacobi symbol or Kronecker of a and n. Turns out to be -1. So am I going to output prime or am I going to output composite? Give me a thumbs up for prime. Thumbs down for composite. What am I outputting, prime or composite? Thumbs up for prime, thumbs down for composite. What do we got? Prime or composite? What am I outputting? Oh, I did not do a good job of explaining this. Okay, here's my check. So I want to look at my power mod and I want to look at the Kronecker symbol. Are they congruent to each other, mod n or not? This one you should know. This one you should be able to do. These two congruent to each other, mod n or not? Yes or no? That one you can do with a thumbs up or a thumbs down. Congruent to each other, mod n, yes or no? No, I'm getting some thumbs down. No, okay, good. All right, now go back and look at your Solovay-Strassen primality test. If those two are not congruent to each other, mod n, do I output a prime or do I output a composite? Those two are not congruent to each other, mod n. So do I output prime or do I output composite? What do we got if they are not congruent to each other, mod n? Prime is thumbs up, composite is thumbs down. Prime or composite? Composite, they're not congruent to each other, mod n. Do we see a composite? Composite, okay, Mandy's saying yes, that's good, okay. All right, and composite, so my answer is guaranteed to be correct. Okay, one more from your notes. This isn't what I typically said, but let's do this one too. So let's say n is 221. This is just my ready-made example of an Euler liar. And if a is 47, I know that I said, oh, a minus 47, sorry. A is 47. I know I said that we usually pick a to be an even number, but I want to demonstrate an Euler liar here. So first thing we'll do is check, well, we'll do the Kronecker symbol. So Jacobi symbol of a and n is equal to -1. So that tells me that a and n are not relatively prime, Jacobi symbol. And then I need to do my power mod again. So a raised to the n minus 1 over 2 mod n, and that's 220. Careful in this case. My Jacobi symbol is -1. My exponent on the other side is 220. are these two congruent to each other mod n or not? Yes or no, congruent to each other mod n. Careful in this case. I've got a -1 and I've got a 220. Are these two congruent to each other mod n? Yes or no? Give me thumbs up, thumbs down. Yes, because n is 221, right? So -1 and 220 are congruent to each other. So these two are congruent to each other mod n, and therefore I'm going to output prime. So I'm going to output prime in this case. But that's wrong, because if I do factor int n, it's 13 times 17. So therefore 47 is an Euler liar for 221. 47 is an Euler liar for 221. I can try another value of a. So let's just try a equals 2 and see if I can get a correct value that tells me actually composite in this case. So let's check the Jacobi symbol of a over n. That's still -1. And we'll do a power mod of a to the n minus 1 over 2 mod n. That's 30 in this case. So those two are not congruent to each other, and this would tell me composite. This is kind of a running theme again with all our primality tests. You can try different values of A, and the more values of A that you try, the more confident that you can be that you're actually getting the correct value out. If you get composite, then you know that it's correct. If you keep getting prime over and over, then you're probably going to have a value that's correct. Okay, questions on the Solovay-Strassen primality test? Anybody, anything?
In general, how's the accuracy of this primality test compared to the other ones we looked at, if you just like do it once?
Yes, I don't know the answer to that, and I'm not sure anybody knows the answer to that. This primality test is not used as much as the others, and so I'm not sure how much research has been done on it. There's no good answer as to why it isn't used as much as the others. It just isn't. And so I am guessing I'd have to do some more digging. I don't have a good answer for you at this point. We know really well about how accurate Fermat's primality test is and how accurate the Miller-Rabin primality test is. And we know that Miller-Rabin is more accurate than Fermat's primality test. And that's why we talk about strong pseudoprimes versus regular pseudoprimes. I don't have a good answer in terms of how accurate Solovay-Strassen is. Sorry, it's a totally fair question, but I don't have a good answer, and I'm not sure if the mathematical community has a good answer either. Other questions on this one? Okay, there is a problem on your homework where there are 3 different values of n, and you need to use each primality test once in order to determine whether you're going to do prime or composite output. So you should be familiar with all of the primality tests. Other questions on the content from today? Okay.